On the backside of our second practice test for the advanced function unit, we are going to start by transforming a graph. In this case, we have the graph y equals x squared, and we're going to transform it with a vertical stretch by -3. Then we are going to shift it with the +2 in the x, which is going to shift it to the left, and the +3 in the y, which is going to shift it up. Let's go ahead and work through these. We have y equals x squared as an interim step working through the parent function with each of these values of x. So x squared, -2 squared is -2 times itself. That is 4. -1 times itself is 1. 0 times 0, 0. 1 times 1, 2 times 2. So we have 4, 1, 0, 1, 4. We're now going to multiply it by this value out here. So whatever we just got times -3, that's going to stretch the graph and flip it. The negative flips it. So we are now going to have a -12. 4 times -3 is -12. 4 times, or -3 times the 1 is going to be -3. 0 times anything is 0, and we repeat with the same numbers down below. And finally, I like to cross out this interim step here because we don't need that step anymore. Our value of x is right here, our value of y is over here, and so we are going to be graphing those points on our chart. Now the -12s are out of range of our graph, so we're just going to graph the -3, 0, -3. So at x equals -1, y is -3. It's a dot right there. 0, 0, and 1, -3. The other points are somewhere around here and here, just for reference, so we can draw something that looks pretty reasonably accurate. And then we need to sketch its translation. I'm actually going to leave those just green dots here. If you have multiple colors, including on your test, I highly recommend it. But we're going to look at the translation. That means it's going to slide one way or the other. When we have this +2 where it used to just be x, what that's going to do is transform x as if we added 2 to it to get what we have now, which means it's actually going to do the opposite thing. So we're going to subtract 2 from every x value. We are going to go to the left. So we're going to go that way, 2 units. So for every one of those dots, I might even just mark a dot 2 units over for each of these, just so that we have references. And you'll notice that that actually overlaps right there. And then we are going to do the 3 up. So the +3 at the end is going to go up 3 units. So every one of those dots is going straight up 3 on the graph. That actually brings these back in range because it went from -12, it goes up 3, up to -9. So these are now going to actually be visible. So we really only need to graph our final one here. So let's do that. Oh, put those back. And we get something that looks like that. Little arrows pointing down. You can see the original, from the original green dots, it moved left 2 and up 3. And that gives us our final position there. So now continuing down to a few more problems, we are going to apply functions and look at where these applications work out. So Jamie put money in a bank account. Every 12 years, the money doubles. So we have money, it's in a bank account. So we have money in the bank account. So that's where it accumulates. And then every so many years, every so much amount of time, the money does something. It multiplies by 2, it doubles. So let's figure out what this all means. Our independent variable of money in years, the one that is the cause here, is going to be the years. And over the years, we accumulate the money. So we are going to put years as our independent variable. the variable that's most likely the cause is the independent. That makes money our dependent variable. That's what we're accumulating. So the money. And now we have to decide is that each step increasing x, x being years in this case, so that's our years, what operation is performed to the previous value of our money. So what do we do to the money value with each year? It says in this problem the money doubles or times by 2. So we're going to search multiply by the same value. So we're going to keep multiplying by 2. And what kind of growth does that line up with? Well, the third option here, the multiplying by the same, that is an exponential function. So when we have an exponential function, that means we're multiplying at each step. Finally, we have one last problem here. We have a child with a bag of chips. Yum. Chips. Great. And inside there's 20 chips, and every day she's going to eat out 4. She's a very patient person. For my child, it's more like every 15 seconds. But, the independent variable in here, we have to identify what our variables are. So we've got chips. They're accumulating inside the bag. There's 20 of them, and then every day something's happening to them. So we start with chips. And that's what we accumulate, and it happens over time. And time is almost always our independent variable. So our days is going to be our independent. And then the dependent variable is going to be chips. So we got our chips there. Beautiful. Chips. At each step increasing x, what operation is performed to the previous value y? It says each day she ate 4 chips, which means each day 4 chips went away. We take away, subtract, not divide, but we subtract 4 chips. So we are adding the same amount every day. And it's hard because it's like, no, we're subtracting, but you can add negatives. So we can plus a -4. If that makes you feel any better about that idea. So we are adding the same amount. We are adding -4 chips a day. What kind of growth is being used for that? That maps onto linear. We form a straight line because every day it goes down 4 in a smooth decreasing function. So let's write our equation for this. If y is our chips, y is going to equal -4 per day plus our starting point of 20 chips. So every day we -4 chip, and then we started with 20. So the stretch, this amount that we scale by or multiply by, is -4 chips per day. So that's what that means. It's -4 times it, so it's chips per day. In the shift, we start plus 20 up as our starting point. And it turns out the whole graph is actually shifted 20 up because otherwise we would be already in the negatives on day 1. So if we're going to construct a graph of this now, I'm going to count my days as my independent variable on the bottom, and I'm going to count that 0, 1, 2, 3, 4, 5, so forth. And then if I were to properly color code this, I'll get to my green here where I have my chips on my y-axis, chips. And I'm going to have to count by something else, so 0, looks like I'm going to have to count by like 5s or something. So 5, 10, 15, 20. And that gives me a starting point of 0 days, 20 chips. So put a big dot right there. After 1 day, I've lost 4 chips, so I'm down to 16. So I'm a little over the 15 here. And then after 2 days, on day 2, I'm down 8 chips, so I'm down to 12. And on day 3, I've lost 12 chips, so I'm down to 8. And on day 4, I've lost 16 chips, so I'm down to only 4 chips left. And on day 5, I have hit 0 chips. And technically, this function could continue, but we know that doesn't really make any sense. So we're going to actually stop our graph because once the chips are out, the fun stops. Now, the domain down here, it says that's looking at the independent variable, the x. So of our days down here, what x values are possible? It looks like we start counting time at day 0, and the chips run out at day 5, so that's when we stop counting days. So from 0 to 5 is when we count. In some functions, we would say, oh, linear function could go on forever in both directions, but in an applied problem, often we restrict the domain to the parts that make sense. So we're not going to have negative days, we're not going to have negative chips. Now our range, same deal. What is the lowest our chips can ever go? In this case, it is 0 chips. The bag is done at 0. And the highest it ever goes is 20 chips. So in our y, our range goes from 0 to 20. And that is it. That's all you need for your functions test. Good luck.